Thank you for having me. I would like to report almost trivial observation to you, which I think has might have an impact on how we see driven systems and statistics of driven systems. This work is done together with three people: Rudi Hanel, who is in Vienna, Bernhard Korominas-Murta, who is now in Graz, assistant professor. And it all came out of work done together with Murray Gell-Mann of this work. All of what I present is published. Little bit of motivation and background. Since 1809, we have the theory of errors. Since 1810, we have the central limit theorem that we all know, that sums of random numbers from distributions with a finite variance lead to Gaussian distributed numbers. If the elements are not too much correlated, this concept entered into physics, which is statistical physics, and it gives us a great handle of all sorts of problems where stochastic variables are centered around a mean. Sorry for this idiotic thing, but just to remind ourselves that if you have a Gaussian distribution, that goes towards zero very quickly. If the argument of this thing is 10, then we're absolutely at zero. Whereas if we look at the fat-tailed distribution, a power law, where the alpha is, for example, 1, if the argument is, this is practically not decaying if you compare it with a Gaussian distribution, something that has a fat-tailed. Complex systems are dynamical systems that are networked, typically where dynamical modes are connected through networks. Complex systems are very often co-evolutionary, that the interaction topology, the forces which can keep track on networks are changing over time as the states of a system evolve. And it's practically no reason why one should believe that Gaussian statistics should play a dominant role in these kind of complicated systems. The statistics of complex systems is basically the statistics of power laws, or something that is close to power laws. If we have variables that are spread out over large space, very often we can talk about. Very often we have these power law statistics present, where outliers are the norm rather than the exception of the processes. This is very important, and of course all of you know about this. Here's a couple of examples where these approximate power laws are present. If you look at the city size distribution, very clear power law tail. You look at rainfall events, how big are rainfalls, how are landslide sizes distributed, hurricane damages in dollars, interbank loans, how are they distributed, how is the financial system composed of things, forest fires, moon crater diameter distributions are very, very, very nice power law. Has to do with fragmentation processes. Gamma ray energy distributions are a power law with a slope of almost 1. Movie sales, healthcare costs, particle physics, cross-sections as a function of particle energies are fantastic power law. Look at the number of orders of magnitudes. Words in books, that's the Zipf, the famous Zipf law. If you're very tired and are reading boring books, you can count the words. And if you are sorting the words according to the frequency, in English books, you will find that the most frequent word is the, second most frequent word is of, etc. if you plot them in such a way, you find a power law with slope 1, Zipf's law. Citations of scientific articles follows a power law in the tail. Website hits, power law book sales, telephone calls, earthquake magnitude, that's the Richter law that we all know. The seismic events that follow a main shock, that's the Omori law, it's a power law. War intensities, killings in war, sizes of wars, wealth distributions, family names, etc. We have not talked about all of these things. Literally hundreds of scaling laws, power laws are found in all sorts of network systems. Networks themselves show power law characteristics in the degree distributions, in the clustering coefficient distribution, in the nearest neighbor distributions. Wherever you look, you find these long-tailed distribution functions. Biology is full of power laws, allometric scaling laws, literally dozens, maybe hundreds of these laws. Many dynamical processes in cities follow power laws, etc. Fragmentation processes, many of you know, crackling noise, some random walks on networks, on structures follow power laws. Bird sightings, fossil records, terrorist attacks. Anomalous diffusion is full of power laws, etc. Is there something like a central limit theorem for power laws? At the moment, not. Let's now focusing on a motivation again. The basic roots to power laws in physics, we know it's criticality. That's where power laws maybe for the first time played a big role in the 1950s, where one understood this so through Murray Gell-Mann, who was maybe the first talking about these things. Self-organized criticality is a part of science where critical exponents, critical parameters are found automatically by a system. It's self-tuning towards these critical parameters, like in sandpile models, where you can think of a slope that adjusts automatically toward a critical slope. Multiplicative processes themselves in pure form do, of course, not lead to power laws. They lead to, if you multiply random numbers with a finite variance, then you get a log normal distribution, of course. But if you introduce some constraints in multiplicative processes, like that you say in a multiplicative process, you don't accept numbers that are smaller than x, and you can get very easily to exact power laws. It was shown by Gabet in a one-liner. Of course, self-reinforcing processes, rich get richer phenomena, these are understood to produce power laws in a very natural way. So I don't talk about any details of these things. There's, of course, other mechanisms that we all know, the Levy-stable processes. These lead to power laws, have power laws, but this is, since this treats independent variables, these are certainly not of the type that we're interested in. When we're talking about complex systems or driven systems, in constraint optimization, extreme value statistics, we don't need any deep theory to understand the emergence of power laws there. I will focus on driven systems and how we can understand power laws that emerge in driven systems. Complex systems are most of the time driven systems. What is a driven system? A driven system is a system that is composed of a relaxation part and a driving part. If you turn off the driving part, it relaxes to some ground state. And let's discuss this a little deeper. So the motivation is, could we find a statistics for driven stationary non-equilibrium system that explains the abundance of power laws or fat tail distributions and variations thereof. Many processes, as they unfold, put restrictions on future states the system can take. Any relaxing system is of that kind. So we call these processes sample space reducing processes, SSR processes. For example, if you have a number of dice in front of you, the first die has one face, second die has two faces, die number n has n faces. And if you think of a process where you start with the biggest die, you throw it, whatever number it gives you, you pick that die. So if you have, it tells 17, you take the die with 17 faces, you throw that, you get a smaller number from 1 to 17, say it's 8, then you go on. And you run through the process until you're converging to the die number 1. Then you restart the process. You pick any bigger die and do it again. And you ask, how often are you visiting any state of the system? Interested in the probability of visiting states. So this is obviously something where the phase space of a system changes over time, gets smaller and smaller over time. Phase space from time to time is reducing. Phase spaces are nested. And if you're driving the system, you have to restart the system, meaning you have to take a bigger die again. Then you are identifying at some point the big phase space again with the smallest phase space at which you restart. An example of a sample space reducing process is how you're forming sentences. We could start with any word of the English alphabet. This is the alphabet. We are picking a word. As soon as we pick the word, grammar and context forces us to restrict our sample space. We can now only pick verbs. Because of grammar, after noun, only verbs are allowed. And since this is a biological thing, we can only use verbs that make biological sense somehow. And the further the sentence progresses, the more and more we restrict ourselves until we come to the point. So to convey information, you need something like a sample space reducing process. I think that this statement is generally true. Here's yet another picture of a sample space reducing process. Here's energy states, for example. And you have a ball that's jumping randomly downward, this staircase. And once it's down to the lowest state, we are restarting it, putting it up to any higher position, and then let it bounce randomly downward. Then we ask, how often do we visit these states? That's the distribution. We always visit state number 1 because that's the sink. And just for comparison, if we don't have such a staircase, we have a ball that bounces left and right with equal probabilities. This, of course, is just a sampling process, unbiased, and gives a uniform distribution. What is this distribution? This is Zipf's law. Easy. There's one thing that we are doing in this sample space reducing process. We are violating detailed balance. That's the, I think, single most important thing. These processes are violating this detailed balance. So the probability to visit state I, if I is this number here, 1 to 10, probability of visiting I is 1 over I. Why is that? That's now why I said this is a simple, almost trivial observation. The probability to be at state I is what? It's the probability that we sit at state J with the transition probability hopping from J to I, summing over all J. And the transition probability from J to I is what? Is that we jump with equal probability to any lower state. That's this part. When we are at the lowest state with probability 1 over n. N is the number of states. We are jumping to any higher state. That's the restarting or the driving process. Okay? And if we plug this in, we get this equation. If we are writing the same thing for one state higher and subtract, we get this relation. This is the difference divided by the difference in p, divided by p on the left side is equal to minus 1 over I. If we take logs, if we integrate on both sides, we have a logarithm in p is equal to minus 1 over I, no, minus when we integrate, we are integrating here difference over p, and here 1 over I, integrating over di. So we're getting logarithms on both sides, and we get pi is 1 over I. Not more than this. Note that in this kind of thing, you can say this is a very peculiar process. We are waiting until the system goes to the lowest state, and then we restart it. We call this the slow driving limit. What if we start the process while it is going down? So with a certain probability 1 minus lambda, we restart at any step in the staircase. We bring it to any other step, and we can show that the probability to visit state I is, again, an exact power law, independent of the size of the system. Already with 3 states, this is true. No asymptotic things. And the exponent is 1 minus the driving rate. It's interesting. Why is it true? Same thing, the trivial eigenvalue equation, if you wish. You're putting in the transition probabilities, you compute this thing, you observe, you have to expand. That's the only trick, but it's an exact result. Just to see it in a minute is if you're expanding this log into this, or writing the log in this sum. Yeah. I certainly agree that this is maybe a clumsy way of showing it, but it's a way that you can also convince high school students with. Certainly true also for the continuous case. Needs a couple of, maybe half a page to show that. Maybe we also did that in a clumsy way. But that's now already a pretty interesting result, which we'll come back to, that the driving rate determines the distribution here. It does not matter really how this relaxation process, I have not shown you that, how that relaxation process looks like. Here is the simulation results. We have slow driving if we are driving only when the system is at the lowest level, and we put it only then into higher states. We get this Zipf law with a slope of -1, no shoulder, all the way straight up to here. And if we increase the driving frequency, 1 minus lambda, the driving frequency, if that is 0.3, then the slope is 1, -0.3, 0.7, etc. How quick are these processes converging to these power laws? They're converging equally quickly as one knows from the Berry-Essén convergence speed. If this is the number of jumps that you're doing, this is a distance from the true or from the expected distribution to the observed distribution. After this and that many iterations, you find that this converges with the speed of 1/√n, or 0.5 here in this slope. So it's equally fast. It's not much slower or anything. What happens if our prior probabilities of visiting states is not uniform, as we have assumed in the most primitive example? If we have a ball that samples these states, of course we are sampling the prior distribution, whatever that is. We'll see in the distribution of states. If we have a sample space reducing process, putting priors on these states, what do we get out? Any guess? No? Zipf's law, Zipf's distribution. It's exactly the same distribution. And now that is getting a little bit more interesting. Let's do the same thing again. It will not get any more complicated, but now we put in prior probabilities on the states, do the same thing. Then we see if the priors, if the probability of being in a state is just by any constraint given by this Q here, if these prior probabilities are distributed in a polynomial fashion, not changing too much from state to state, then we get Zipf's law. Lambda is here the driving rate. It's exactly the same result as we had before. If we have priors where the polynomial, when they are distributed with a polynomial that is falling off quicker with a power of alpha than -1, then we are sampling the priors. Is clear because we are just sampling so often. And if we have exponential priors, meaning that that we're practically jumping always to the next lower state because the next lower state is exponentially, is always the biggest with the highest probability we will always go to the next lower state, then we are sampling just a uniform distribution. And we are sampling every state in these cascade processes. And that's then uniform at the end. So but the message is, as long as the prior probabilities are not pathological, or not too different from each other, we will always observe the Zipf's law or this exact power law in the distribution function, no matter what the details of the system are. And that's, I think, it's an unexpected situation. Now, a driven system is composed of driving and relaxation part. The relaxation part of any system, we think, is a sample space reducing process. So here the generality comes from. Details of the relaxation process, it does not matter. If we're not having all the states present, I'll come to this in a second, with an example, situation does not change. Not all transitions must really exist. This reminds immediately on diffusion processes on networks. On networks that are directed, where diffusions happen from one node to the other along a directed link. Yeah, it's obvious that this kind of process you can map into a network where you're connecting higher states with lower states with pointed directions. And then if you have a diffusion process on such a network, you will always get a visiting distribution on the nodes. That is a Zipf law. So these kind of networks are called, they have a famous name, directed acyclical graphs, means they have no cycles in a network. So this is a graph with cycles. This is a graph that has some order on it. And let's say we introduce directions in this graph where we go from higher states to lower states, exactly in this kind of fashion that we had before. Then we are introducing directions. And now we don't have cycles anymore. We don't have directed cycles anymore. It's an acyclic directed graph. If we now put random walkers on this and ask how, and let the system run and relax, restart it, relax, and ask how often are the states visited, we get Zipf's law, the prediction. This is the result. If we take a random graph as the simplest example for a network, put a direction on it in the way I prescribed. If we let diffusion run, we get the visiting distribution as a power law with slope -1. If we are taking a different network structure, also kind of completely non-intuitive, if we're now looking at an exponential network that's very different from a random graph, or a scale-free network that is totally different from a random graph, if we put the network of high-energy physics co-authors, which is no matter what you use, if you put the direction on it and let random walkers diffuse, you always get Zipf's law in the visiting distribution. And once we have the visiting distribution from a statistical mechanics point of view, we know the statistics of the system. We're only looking at, we're not looking at dynamical processes. So this is an example of what I meant before, what I showed you before with these prior probabilities. These prior probabilities don't matter. Also, if the network is not fully connected, that does not matter. If we take out many transitions that are not possible, doesn't matter. Now, take a random graph, and let's put weights on the links. And the weights are now proportional to how likely it is to diffuse along a link. Introducing now another type of bias into the network. If we are taking the link weights from a Poissonian distribution, we get Zipf's law. If we are taking the same type of random graphs but put power law weights, power law distributed weights on the links, we get exactly the same distribution. It's also tough to swallow. If we are introducing cycles in the network, then what is happening? Then we effectively are bringing lower states to higher states. We are driving, that is related to the driving rate, and we are changing the slope. So by measuring the slope of state visits in a network, we can measure the number of directed cycles in a network. And 100% in line with these simple equations that I showed you before. So this Zipf's law, or these power laws, exact power laws, if you drive faster than slow, is an immense attractor. No matter what the network topology looks like, no matter what the link weights are that govern the diffusion processes, you always get exactly Zipf's law. If you have cycles, you get an exact power law. A few more examples. Every search process, if you do a good search process, when you look somewhere, you try to exclude lots of space where the thing that you're looking for can be. You're reducing your sample space by every look that you take. You exclude the possibility that you have lost your keys there. How can one measure search processes easily? By looking how people look for stuff on the internet. This is a classic plot, 20 years old, of the click rates of websites. If you rank the clicks, so the most frequently clicked pages here was clicked so many times. Internet was not so big 20 years ago, so this is not such a big number. But this is a Zipf's law. Exactly what we would predict. Now you say, there's a lot of randomness going on how people click on web pages. Of course, that's true. But if you look at how people in the professional world are looking for things, companies very often have, when they are doing programming as their business, then they have repositories where you can find code parts, etc. And you're looking for those. People are looking for those. If you look how people are searching for professional things on web pages in companies, in big companies, like, I don't know, DEC, that was a computer company long time ago. Is there anything else? These are early day tech companies. And if you see how people are searching for things, Zipf's law. And there's no doubt that if you're looking professionally, searching professionally, that this leads to Zipf's law. What about exponents between -1 and -infinity? So far, I've only showed you possibilities to generate power laws between 0, uniform distribution, to a slope of -1. Driving rate cannot be higher than 1. How can we get higher exponents? If we have a process, the same situation, ball only goes to the left but jumps random directions, and now before it jumps, it multiplies. It multiplies with the multiplication factor mu. Before it jumps, it splits into mu other balls. If mu is equal to 2, we have this picture here. This ball jumps, multiplies into 2 balls, both jump down independently, and before they jump, they multiply in 2 and go down. Now it takes a little bit more work to show that the probability of visiting the states I is proportional to I, not proportional, it's exact. Oh, it's proportional. There should be a constant. Proportional to I to the negative multiplication factor. If we're not driving, if we are slowly driving, otherwise it gets more complicated. But it is really the case. We can show you in simulations here. We can also show you on paper that this is true, maybe in a clumsy way. Interesting. What? Yes, keep increasing. Isha. Yeah, so let's do this for many, many times. Good. But so everyone who reaches the lowest state, we're putting into the system again, and just keep going. It will, with the number of particles, will blow up, but they go down, and it's just more of them, and it will not change the distribution function. If you don't normalize, it will explode. But now this reminds us on hadronization processes. One muon coming into the atmosphere, splitting into 2 muons, etc. Here we have energy conservation. What if we introduce conservation laws? What do I mean by that? If these are energy levels here, and if the energy of 14 plus energy of 17 gives kinetic energy of 20, we have a conservation law. If we implement that, we need a page, and then we can show you what. We can show you that the exponent will always be 2, -2. Nice? This is Fermi's result of the cosmic ray energy distribution. Is it true? Of course not. But Fermi is equally wrong as we are, 2.6 or something in reality. Big debate still why this is the case. But we can do Fermi's result, we can derive not based on physics, but just as a statistics result, and plus the requirement of conservation laws. Conservation laws is a lot of physics, so this is, of course, where Fermi's result comes from. So if you simulate, you get this. I think I've said this. Here's one more thing that you can test experimentally. If you have a foil gold or something, and you're shooting neutrons in. You have neutrons with a fixed kinetic energy. And as the neutrons will hit atoms in this matter thing, it will lose kinetic energy. And if you are measuring this kinetic energy after they exit this piece of material, what do you expect? The energy distribution should be a power law with -1. People have been measuring this since the 1920s, and maybe before that. Comes out very nicely. Don't confuse this with the penetration depth, which is of course exponential, but is perfectly in line with the energy distribution. And show that both of them need each other. So that's not a new result. It's just to show you that where these kind of things apply. And maybe as a last example, if we have inelastic, if you have a gas where the gas atoms or molecules collide inelastically with a coefficient of restitution of less than 1, we can ask, what is the energy distribution of these gas particles? Classic problem since Boltzmann's times. And how do we see this problem? The energy distribution is what? The same thing as we had before. It's the energy distribution of the gas particles in the container times the transition probability that you go from E to a lower energy, E prime, summing over all energies, plus we need a driving process, which we can include in 100 different ways. If we just say that whenever a particle hits a wall, it gets a kinetic energy boost, or it gets a kinetic energy from this distribution here, then you have implemented it. Now you can try to, all you need to do is, this is not the Boltzmann equation, this is just a primitive transition rate equation or eigenvalue equation. You have to specify this thing. Now you have to do some work. You have to compute this. You have to integrate out all the angles of the collision. But you can do that. Ugly expression. Here you are introducing the fact that you are jumping to lower kinetic energy states. And you can computationally solve this equation. This is the results that we get. Energy distribution for different, I think, total kinetic energies that we are comparing here. Here is the Monte Carlo result for the same box, for the same driving process, and we can, where you see clear, what is this distribution? This is the Maxwell Botzmann distribution for inelastically scattering particles in a box with a very primitive driving. So there's a large region where we have an approximate power law. It's not a large region. Here we have something more complicated. Here we have the Boltzmann-Maxwell shoulder. This part and this part we can fully understand with solving this eigenvalue equation, which we think is cool. We don't need a Boltzmann equation ansatz for solving this problem. This is for different driving rates. Driving rate determines the power law. Our theory predicts that for different coefficients of restitution. Different, and the dots here is the simulation results. The red curve is the theory. Of course, we had to solve this equation numerically. No way of doing this analytically. Last thing, if the driving rates are not homogeneous in the system, but depend, if you could describe them with a function, driving rate function. No, 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 no. No, I've given you everything. It's crystal clear. I've not hidden anything. No approximations, nothing. This transition probability. Yes, yes, yes. No, we're not questioning Boltzmann's framework. We're just saying that for the case that I describe here, you can solve this transition probability equation, and the outcome is what I've shown you. And we all know we. The inelastic thing is there because we put the geometry of the inelastic equations in this kind of this bookkeeping exercise, which you can maybe criticize if you find an error, but otherwise, this is a crystal clear thing.
You assume the is homogeneous in space.
It's an assumption, and we know that these driven systems depend on maybe the form of the container, in some extreme cases, of course. It's a small cylinder or something. It depends on the driving rate, which we can control for, which we can explain. It depends maybe on the size of the system. But all these things are parameters in our equation. If you don't like it, I can also not do anything else, but suggesting that you read the details and criticize us in detail. Just a last comment. If the driving rate is a function, 1 minus this thing is the driving rate, we can relate this this function with the distribution function, which again is nothing else but trying to work out what is the transition probability. Now with this lambda that is a function of the states, and it becomes a little bit more difficult, but not more than 5 lines. And now you can go through this driving rate function and ask, what if this thing is a constant? If this constant is 1, work it out. P is Zipf's law. That was the first example I showed you. If this lambda is homogeneous, if you're driving with equal probability at every state, which is certainly true for many systems, this is a constant, different from 1, or 1, doesn't matter, you have an exact power law. If this is linear, you get the exponential. If you have linear plus an intercept, linear plus a constant, you get the gamma distribution, which you mentioned. If it's quadratic, you get the Gauss. If it's any power, you get the stretched exponential. If you put the logarithm plus constants, then you get the log normal, etc. Whatever you want, you can formulate it in form of driving rate. And that's, with this, I leave you alone. I think the thing that this simple observation teaches us, it might be really the case, or there's this evidence, that the details of the relaxation process don't matter that much in understanding the observable distribution functions of a system, or the distribution functions that determine the state visits of a system, and that the dominant part comes from the way we are driving the systems. I think that's cool because it introduces some generality that we did not expect for, at least we didn't.